Now, if you remember from the end of our talk yesterday, or 2 days, I think it was 2 days ago, that in order to predict the stability of the nucleus, we were looking at the ratio of the number of neutrons to the number of protons. And we stated that down here, right here, this red line is a 1-to-1 ratio. So that red line's the 1-to-1 ratio, and we stated that the lower the elements, the smaller the elements, the lower the number of protons, then they were stable. The nuclei was stable at more of a 1-to-1 ratio. This is what we call the band of stability right here. As you go the band of stability, these get more and more stable at a higher ratio. So these ones up here are a 1.5-to-1 ratio. Down here, this says 10, a 1.4-to-1 ratio. So we were looking at the ratio of the the neutrons with the protons. Today we're going to talk a little bit about nuclear change. We're going to start our discussion with this. We will not finish it. We will finish it next week. But we're going to talk about some different ways that the nucleus will change to achieve that stability. Radioactive decay is the spontaneous breakdown of unstable nuclei to produce particles or energy. It involves the release of particles, the release of electromagnetic waves, or both. We're going to discuss, first of all, stabilizing the nuclei by converting neutrons to protons. Stabilizing the nuclei by converting neutrons to protons. Now, just like I told you a little bit earlier, the stability of the nucleus depends on the ratio of neutrons to protons. We call that the N/Z number. If there is a large N/Z number, or too many neutrons, the nucleus will decay and emit radiation. So if N is too large, the nucleus will decay and emit a radiation. A neutron in this unstable nucleus will emit a high energy electron that is called a beta particle, represented by this Greek letter B. That looks like ours. That's a Greek B. A beta particle, and change to a proton. So what happens is, we know that the nucleus is unstable. One neutron will emit a beta particle, which will change that into a proton. That process of emitting this beta particle is referred to as beta decay. So, if I'm looking at this diagram right here, okay, I'm looking at this diagram right here. Neutrons are blue, protons are green. I can see that this is carbon-14, so that means that there are 6 protons and 8 neutrons. When beta decay happens, and if you see it was this, my arrow right there is on that neutron, because that neutron has gotten rid of a high energy electron that is called a beta particle and changed that neutron into a proton. Now, if that happens, do we still have 6 protons in carbon? If we changed a neutron to a proton, that means we have added a proton. So we went from 6 protons to 7 protons. So what is 7 protons? Nitrogen. Now, did my top number change? Why did my top number not change? Why? That number, that top number, is the number of protons plus the number of neutrons. So that top number did not change. There's still the same number of protons and neutrons. However, the bottom number changed. The atomic number changed because we have a neutron that is converted into a proton in the process of beta decay. So if we look at this, this is just a real generalized equation of what is happening. Okay? But basically, a neutron in the nucleus is converted into a proton with a high energy electron called a beta particle being released. So once again, as a result, that carbon-14 now becomes nitrogen. Now, this is the process. I'm sure at one time or another you've heard of carbon-14 dating. Okay, this is the process and determining how much of that carbon-14 has been converted to nitrogen. Okay, this is how they date older items based on half-lives, and we'll talk about half-lives later on next week sometime. So there we have it right there, the equation of the carbon converting to nitrogen with the beta particle being released. A second way we can stabilize a nucleus is by converting protons into neutrons. Kind of the opposite of what we just did. Converting protons into neutrons. Now, if we're looking at this particular process, and we're talking about that N over Z number, the number of neutrons compared to the number of protons, in this particular situation, the number of protons are too high for the stability. Okay? So, the nucleus has too many protons, and it will undergo a process that is called electron capture. What happens is the nucleus absorbs one of the electrons from the atom, usually one from the 1s orbital. Why would you think that? What do you know about the 1s orbital? Why would you think that the nucleus would absorb an electron from the 1s orbital? Any ideas? How about that it's the closest orbital to the nucleus? Okay. So the nucleus absorbs an electron. In that process, a proton is converted into a neutron Therefore, the atomic number is decreased by 1. The atomic number is decreased by 1. Does the mass number change? No, once again, the mass number is the same because the mass number is the number of protons plus the number of neutrons. That does not change. So, when I look at electron capture, okay, when I look at electron capture, right here I have carbon 11. If I know carbon 11, what does that mean? Well, that means that I have 6 protons, and I have 6 protons and 5 neutrons. 6 and 5 make 11. Carbon is 6. Now, here is that electron. Here is that electron that is being captured. So as that electron is captured, you can see that this proton right there is converted into a neutron. I still have an atomic mass of 11 because protons and neutrons are still 11. However, I now have 6 neutrons and I have 5 protons. Well, what is the element on the periodic table with 5 protons? Boron. So this is now boron. This is now boron. Now, okay, now you can see right here that I'll let you copy it down first. A typical nucleus that decays by electron capture is krypton 36. So if you look right here, I have krypton 36. Has atomic number of 36, a mass number of 81. So as I have the electron being captured, I can see that this 36 add electron, the electron changes a proton to a neutron. So now I have 35 protons. What element has 35 protons? Periodic table tells you that it is bromine. So by electron capture, this krypton is stabilized. The nuclei of that krypton is stabilized, and it is converted into bromine. Now, the big part here is, and you saw on the last slide, it said neutrino. Well, this right here, it says the final symbol of the equation is the release of gamma rays. If you remember a couple of slides before, we said that there could be a release of particles, there could be a release of electromagnetic radiation, or both. Well, in this case, a gamma ray is electromagnetic radiation. Okay? Many nuclear changes leave a nucleus in an excited state. When the nucleus stabilizes, it then releases that energy in the form of these gamma rays. So the nucleus, when that change occurs, is in a bit of an excited state. That energy is released in the form of gamma rays. Gamma rays are also released or emitted in a process that we call positron emission. So if you think about this, okay, the first one was beta decay, the second one's electron capture. This one here we're going to talk about is the third one, positron emission. Once again, positron emission is where there are too many protons in the nuclei. So the N over Z, the Z is too high. What happens is we emit what we call a positron. A positron is the antiparticle of an electron, the opposite of an electron. This process is very similar to electron capture because a proton is once again changed to a neutron. However, when we have that proton being changed to a neutron, we emit or we give off the positron. We stated that a positron is the antiparticle or the opposite of electron. So when this positron is emitted, it collides with an electron. Anytime a particle collides with its antiparticle, all of the masses of the two particles are converted entirely into gamma rays. So that collision causes the release of gamma rays. Once again, gamma rays is part of electromagnetic energy. So when those two particles, the positron and the electron, collide, it's called the annihilation of matter. That sounds pretty serious, doesn't it? Annihilation. Now, as we look here, I rewrote these up here because this is kind of hard to see here. I rewrote it, but this is chromium. Atomic mass 49, atomic number 24. Okay. What has happened is due to the instability of the nucleus of chromium, one of the protons is converted to a neutron. So we go from 24 protons to 23 protons. Atomic number, once again, does not change because it's the number of protons plus the number of neutrons. So we go from 24 protons to 23, and we give off a positron, which is symbolized by this 0 over plus 1 e. So it shows you that it is the antiparticle. Right here is a positron that was just formed here. So that positron that was just formed then collides with an electron right here to give us the total mass being released in the form of gamma particles. So all of the mass from that positron and that electron gets released in the form of gamma rays. So it is dealing with creating stability and releasing energy, this positron emission. Okay? So basically what we have dealt with today is we've dealt with beta decay, we've dealt with electron capture, we've dealt with positron emission. Tomorrow, or not tomorrow, next week, we are going to discuss alpha particles. And then I'm going to show you some of these equations, because probably the main thing that you're going to have to do is to be able to work some of these simpler equations and to recognize, okay, what is happening here? Okay, we've talked about 4 different types of nuclear change. This equation is showing me what type of change.